also a PhD student in University of Basel at the group of Professor Martino Poggio. And what I will present you today is imaging that we did using superconducting scanning squid microscopy on chromium sulfuromide. And more specifically, what we want to see is how the magnetic reversal is affected by a strain, an inhomogeneous strain on the material. So, based on the people that are here and on the previous talk, I think I can skip a bit the motivation on 2D magnets and antiferromagnetism in general and save some time. And I want to start by telling some magnetic characteristics of this material for the people that are not working yet on chromium sulfuromide. So it has an orthorhombic structure, as we can see, and the magnetic moment comes from the chromium atoms that are interacting between each other with super-exchange and super-exchange mechanism. It is an A-type antiferromagnet, meaning that the spins are aligning ferromagnetically in the plane, but we have a ferromagnetic coupling between the different layers. Also, it has a biaxial anisotropy with the z-axis pointing along the crystallographic B direction, while intermediate and hard axes are along the A and C axes. Finally, one reason also that this material is very interesting, apart from all the properties that we have seen so far and we'll probably see in the next talks, and more specifically on the magnetic characteristic, is that it has a relatively high near temperature. It has small switching fields in contrast to bulk magnets that are usually have switching fields more than 1 Tesla, while also it's a very stable material in contrast to other 2D magnets. Because now it has a very anisotropic crystal structure, this also gives a very particular shape when you exfoliate it, which looks like a ribbon, as we can see here, and a long edge, with a long edge being along the A axis and a short edge along the B. So we know that 2D magnets in general are very susceptible to external stimuli like doping that we saw yesterday, also on the specific material. But what I want to talk about is strain. So from a study that they did in 2022 at Columbia University, they found that when they applied uniaxial strain along the A crystallographic axis by using a strain cell, they could induce a reversible and controllable antiferromagnetic to ferromagnetic phase transition when the strain was exceeding roughly 1%. So the way to understand this, we can imagine the changes that happen to the exchange pathways of the interlayer coupling. And more specifically, we can see that the energy difference between the ferromagnetic and antiferromagnetic configuration in the interlayer coupling is changing with applied strain. More specifically, tensile strain decreases the antiferromagnetic coupling, interlayer coupling, eventually going to a phase transition under high applied tensile strain, while compressive strain increases the antiferromagnetic coupling and like that, increasing the switching field that is needed to polarize it. So we see that this material is very susceptible to strain, and its magnetic properties are affected by that. So what the questions that are naturally arising are, can we, what's the local magnetic behavior of this material during reversal, especially when you have strain inhomogeneities in the sample, while also is it possible to confine the magnetic reversal in a specific location and control its evolution if we create some strain gradients in the sample, while this maybe could explain inhomogeneities that are observed in previous studies during magnetic reversal. So these questions I will try to answer with the imaging that we did. But before going there, I want to talk a little bit about the technique that we use, which is superconducting scanning squid microscopy. And this is a technique that exists since the 90s. However, we have implemented some new sensor in our lab, and I want to show you a bit what is the differences with what was done so far. So we know that squids are very sensitive, the most sensitive magnetometer actually that exists, with the electrical properties being very sensitive to the changes in the magnetic flux passing through the squid loop. So back in the 90s, they thought to create some scanning device, so creating a squid on a planar geometry, and then using it to scan above a sample and measure its magnetic field locally. These first devices were very big, the squids were very big, and also because of their geometry, they couldn't approach very close to the surface of the sample. And what does that mean? It limits the spatial resolution, so you cannot see magnetic features on the nanometer scale, while at the same time, we can also not go close to the surface. And if you have a small magnetic field that is rapidly decreasing with the distance, since the field lines are diverging, you will not be able to measure it. A big breakthrough in the field came from the group of Professor Eli Zeltov in Weizmann Institute, when they managed to fabricate a squid on the tip of a pooled quartz tube. And with this method, they managed to go down to a spatial resolution of roughly 50 nanometer, while also they achieved a very good magnetic field sensitivity down to 5 nanotesla per square root of hertz in the white noise regime. I don't want to go to the detail for this, but using this technique is very challenging, and I think it can really, actually, members of our groups also use it, but their life is very difficult, and this is because it's very risky to approach to the surface of the sample and scan above it without the risk of crashing it. And in order to make our life easier, we thought of combining the squid with atomic force microscopy. And like that, to have a very robust approach at scanning above a sample. So quickly how we do that, we take a commercial AFM cantilever, atomic force microscopy cantilever. We cut away by milling with focused iron beam the tip of it, creating an apex. Then we're depositing our superconductor, which is niobium in this case. And finally, we go back to focused iron beam and cut a trench up to the apex and create the squid loop there. This is an actual ACM image of the first squid that we fabricated, and I zoom in on the apex of it. So we can see that this trench here separates two superconducting leads, and here we can see the squid loop and the two Josephson junctions. I don't know if you can see them very well, that are created because of the constriction of narrow constrictions. So the very first squid that we fabricated was around 350 nanometer, but we managed to scale this down. Again, I don't want to go to detail of that, but just measuring the the electric characteristics of our squid under external applied field, we can calculate a magnetic field sensitivity that goes down to 10 nanotesla, similar to what was done from Eli Zeltov's group. So very quickly, through the years from 2021-22 that we first fabricated it, we managed to downsize it, firstly to 140 nanometer by, again, using gallium focused iron beam, but then through a collaboration with the groups of Dieter Kohle and Armin Noll, we managed to create squids that were going down to 6 nanometer effective diameters by using helium and neon focused iron beam. So very quickly, our setup, and as we can see, we can do, by the interferometric setup, we can take the topography of our sample, so non-contact AFM mode. But the thing that we're mostly interested in is the magnetic signal, where by measuring the raw signal of our squid, we can do mapping of the out-of-plane field that goes through the squid. Also, we're oscillating the cantilever at its resonance frequency, and like that, we can measure, we can demodulate our signal on this frequency, and like that, do spectral filtering, avoiding 1/f noise. And it's also actually this method better in order to resolve small spatial features. And because of these reasons, I will show you in the next slides this magnetic field map, which is actually proportional to the spatial derivative along the z direction. So this squid that we used was still not the best spatial resolution that we achieved, since the study was done a bit earlier, and we have a spatial resolution of around 200 nanometer. Okay, finally going to the actual study. So we used the sample that we got from the collaborators in Colombia, from Corey Dean and Xavier's Roy group. And what they did is they took a chromium sulfur-bromide flake that has, again, as we said before, this ribbon shape. And by using a micromanipulator and an AFM cantilever, they pushed the micromanipulator on the one side of the flake, and like that, creating a bent structure. So what is happening now, we have a bent flake that has tensile strain on its left side and compressive strain on its right side. This is the actual AFM image, atomic force microscopy image, topographic image of our sample, that we can also even see that due to excessive bending, the flake has been broken on this part. And the white dust outline shows the original position of the ribbon. So based on the topography outline and by calculating the local radius of curvature, we can calculate how much strain is induced to our flake locally. And we can see that we have a maximum strain around these positions, tensile and compressive, of around 0.25%. So based on the study that I showed you earlier, 0.25% is not enough to induce a differomagnetic to ferromagnetic phase transition. So what we would expect to see is, if we don't apply any in-plane external applied field, is that the flake would still be found in a differomagnetic configuration. However, and actually, this is what we see when we don't apply external applied field, and we can see that we have almost no magnetic contrast, which is what we would expect, but we see a small magnetic contrast along the right edge of the flake. In order to explain this behavior, we go back to the topographic image that we have, and we can zoom in on a specific area, and we can see that we have a non-homogeneity in thickness along its right side. By taking now the line scale, we can see that most of the flake consists of 18 layers, but we also have a narrow strip going to 19 layers and finally dropping down to 14 layers. So based on this, what we expect is that the 14 and the 80 layers, that is the majority of the flake, the magnetic field from there will completely compensate the field lines and will produce no magnetic contrast, while we will have some magnetic contrast coming from the field lines produced from the narrow strip. And this is exactly what we see here. So this magnetic contrast comes from the narrow strip on this of the uncompensated layer. So, okay. And now what we actually want to say is, okay, this strain is not enough to introduce a phase transition. However, what happens when we start applying a field? Here I have overlapped the FM image with strain gradients to be able to map a bit the regions with a different strain. And by starting increasing an in-plane applied field along the easy axis of the material, so along the x direction, at 200 millitesla, the configuration is the same. So we have a ferromagnetic coupling throughout the layers, and the narrow strip is pointing against the field direction. By increasing now a little bit the field further, we see a magnetic contrast created almost to the full, along the full flake. However, there is a small part up here and also a small part on the right edge of the flake that is still not fully flipped. So what is actually happening is that we have a layer that has flipped, and we think that it's also the surface layer based on the same reason that Yao explained yesterday, since it's only coupled to only one layer, so the bottom layer is only coupled or exchange interactions with the top layer, you have a smaller switching field compared to the inner layers. But also that this transition is not fully happening, and we still have some part of the flake that has not flipped yet. Increasing now the field further, we see that the bottom layer now has fully flipped. So we see the contrast at the edge of the flakes, while also from a very small magnetic contrast that we see on this side, the red magnetic contrast, we also understand that the top flake also flipped. Increasing the field further, we start reorienting the inner layers. And what is very interesting now is that we see that this happens from the region of the maximum tensile strain, which agrees with the pictures that I described before, that the tensile strain decreases the differomagnetic coupling, so it's easier now to polarize it. So yes, what we see is that a transition, a differomagnetic to ferromagnetic transition starts from this region, and by applying a higher field, this contrast expands along the y-axis. So actually, it really follows the transition from the maximum tensile strain to regions with smaller tensile strain, so the smaller strain gradients that we see. And going further, we see that the contrast keeps on expanding, but at the same time, we have a higher magnetic constant in the middle, which is again the region of the most tensile strain. And this means that also we have extra layers that are starting to reorient as well. Finally, increasing the field further, more layers are flipping. The contrast expands along the y-axis. And finally, at higher fields, goes towards the position of the compressive side. So it really follows the strain gradient that we see from our model. And finally, we're reaching a saturation of around 400 millitesla. How much time I have?
You still have 4 minutes.
4 minutes? Oh, OK.
Which is bad or good?
Bad, but I will try to speed up. OK, so we can also better understand this magnetic reversal by taking some local, by measuring the local behavior. So we're taking an average area here. We're averaging the field plot now, and I'm telling you how much is the average strain on these areas. And we're plotting its magnetic field against the field applied along the z-axis. And what we see is a very strong correlation of the switching field increasing, going from the most tensile region, so the red, dark red plot, towards the blue, very dark blue plot, which is tensile strained. So, OK, we understand the behavior. However, we want to also compare it to the behavior of a pristine flake. And that's what we do. We're trying to we found a flake that has the same thickness, 18 layers. Actually, it even had a narrow strip along its right side. And we also applied an in-plane field along its z-axis. So starting increasing, in the beginning at 0 field, we observed that we have the same configuration that we had on the strain flake. And by increasing at 200 millitesla, we see that the top strip now reorients first. And this is because we don't have compressive strain as before. while continuing further, we see a very sharp transition of the first layer of the bottom layer flipping. So note this wiggling that we saw in the previous case. And increasing the field further, we start seeing magnetic contrast on the edges of the flake, in contrast to what we saw before that was in the middle. And this also expands throughout the x-axis of the flake. So we don't, it's not condensed, confined on the right side of the flake. This contrast starts increasing from the edges towards the middle of the flake, as we can see, and also during this process, more layers start flipping. Finally, reaching a saturation of, again, around 400 millitesla. Doing the same analysis as before, now the regions that we choose are not related to strain, since we haven't applied any intentional strain to the material, and we want to see what's their local behavior. We see that there is no correlation between right and left side, so the red and blue curves are kind of overlapping. However, as we saw before, we see a trend coming with an increasing switching field coming from the edge of the flake and going towards the middle. Comparing the two behaviors overall, we see that the switching starts earlier on the strained flake because of the tensile strain that decreases the switching field, and also we have less inhomogeneities on the pristine flake. Okay, finally, in order to understand better the behavior, we also performed micromagnetic simulations using MUMAX. So we assume the geometry of our flake, material parameters, and in order to induce the strain in the behavior, we modulate, I took the strain map and translated to an exchange in the layer exchange gradients map. And I included this in my simulations. And what I saw is that I could very nicely match the behavior of the experimental hysteresis to the simulated hysteresis. If we also see spatially what the simulation showed us, for example, I chose just two maps on 320 and roughly 375 millitesla, we see that many characteristics of the maps are also reproduced. For example, we see that the most contrast is on the most tensile strained part, and some more flakes have expanded further. And we also see these wiggle parts that we also saw in our scans. Now, because of such a nice match, we can also see a bit the magnetization that the simulations gave us. And here I'm plotting the overall magnetization throughout the flakes, where we can see a higher magnetization on the center, which is the most tensile strained part. And if we see now what happens layer by layer, is that we see this waviness, wavy characteristics also in the magnetization maps, while at the same time, different layers have reoriented a bit differently in the different layers. The reorientation happens a bit differently. Okay, so overall, we studied the effect of strain gradients that had on magnetic reversal of chromium sulfur-bromide. And we could really link the domain formation and evolution to the strain gradients that were produced in the sample. By using a micromagnetic model, we reproduced the magnetic hysteresis and spatial magnetic features, giving us a bit more insight on what is happening. And finally, we also think that maybe, okay, there could be other effects as well, but maybe the behavior of the pristine flake is also affected by strain gradients that could be, in principle, produced through the exfoliation and fabrication, also during when we're stacking materials. Like, we know that this can all affect the behavior. And we think that this is very important, since we know that these materials are so affected by strain, that maybe this should be considered when we really want to do applications on how the behavior is affected. So I want to acknowledge the group members, the members that I worked with on this project. So my former postdoc Kuzik Pagani, Daniel Yetter, and Boris Gross, and also the groups of Xavier Roy and Corey Dean from Columbia that provided us with a sample, and Patrick Maletiski, through whom this collaboration became possible. Thank you for your attention.